So Kevin is going to show us about graphics and visualization. Metzley is going to, can you mute your computer?
I'm trying.
Yeah, no worries. Okay. Metzley's gonna do accuracy and speed on Wednesday. And then next Monday, we have off. So let's go, baby. Um, and then we'll sort of move very quickly into using the computer to do derivatives. And that will allow us to start thinking about physical concepts. In order to start thinking about physical concepts, we have to think about how we display them. So we will get a little bit of a tutorial here from Kevin, but really you are going to learn about visualization the whole time, right? So make sure that if there's something that you really want to dig into in how you present or plot, this is the time to do it. You'll see some options that are in the book. We won't use all of them. Okay. Some of them, they're a little outdated. Okay. So, do you want to present something and then I'll put it on the screen here?
Go ahead and do that. Share.
Well, so we can do this in one of two ways. So we can show, I can show the book and you can talk through the book, or if you want to talk right through your.
Literally have comments through my code, so I was gonna.
Okay, perfect. Let's do that. Whatever's clever. Good. Everyone see that okay? All right.
Okay, so today we're gonna talk about how to make graphs, right? So we first start off with importing, right? So from PyLab, you have to import a plot and then show. And then we have here on our data is y equals, and then we have some numbers. This is just gonna show you, and then you plot y, right? So this is gonna show us the graph of those numbers. If you notice, our x-axis, there's no like discrete x numbers here. It's just labeled from 0 to 5 because that's how many inputs we have. We have 6 total inputs. To show discrete numbers, we must label both axes, right? So we do the same thing, but now we have an x-axis, right, or x data. So when I input these numbers, these values for x and these values for y, you plot x and y, you show it, and here's our data, our graph here. Okay. You see that we now see specified numbers instead of 0, 1, 2, 3, 4, 5, etc. So you can also save this graph. It's in the book. It says you can click on the graph and there should be options on the bottom, but I didn't see it. So I don't know how to save the graph. Oh, just kidding. No, I don't know that. I don't know how to save the graph. In the book, it says you can save it.
Yeah, you can save it. There's a different command if you want to save it as a PNG or something, but we won't use that as frequently because you're not, unless you need it for something else. You're going to use just the folder you're in.
So yeah, once you save it, you can zoom in on portions or move around the graph, etc. And then we go into a much more complicated graph that just it's actually a function now. So you have from PyLab, we import the again plot show, and then from NumPy, we import line space and sign, which is our function, right? So here, x equals our line space and then our values from 0 to 10, and then y equals sign x, which is our function. And then you plot our x and y and you show it, right? So this is our actual sin x graph. And you can also, I also said that like, I don't know how to do this, but you can also input data from a computer file, like a TXT file. And if you go back to the book on page 92, it has it listed. Here's some values.
On page 92?
Yes.
Okay.
As you see on the left there on page 92, you have a set of data. So from 0 to 7, and then it has data values. You can import that and put it onto a graph, right? You do that by importing load text and then from PyLab import plot show, and then your data equals load text and then the name of your actual data set, right? And then float. And then it should show you a graph like the one on page 93. So yeah, we can also use this load text function from NumPy to read values and put them in an array. This extracts the first and second columns of the array and puts them in a plot. Notice though, something we do know is that the code stops once it reaches show function. This is called a blocking function. When working with graphs, we will sometimes not know all the values for a graph initially, but find them by some calculation in a different code. So like here's an example of the sign graph that has individual values and adds them to a growing list. So again, we import PyLab import plot show, from math import sign, from numpy import line space, and then here's your x points, your y points, right? And then for x and line space, we do the same thing, and then append your x and then append your sign x, right? And it should give you the same graph as we had before. This is just a different way of writing this one,
Okay.
right?
Let me stop you there for a second, Kevin. So for folks who maybe haven't worked with this yet, what is the difference between line space and range? Okay, interesting. Number of iterations, right? So for range, it says something like start, stop, and then what's the third one? Step, right? And so for this, you would expect them to go 0 to 100 in steps of, or 0 to 10 in steps of 100. But that's clearly not what happens in line space. And to your point, you said something like 0 to 10 with 100 iterations, right? So what that means is break up this by 100. And if I look here, it goes from 0 to 10, just like I would expect, and it's nice and smooth. Go ahead and make this into like 4, right? And what's going to happen? All clumpy, right? Really shitty.
Right here, this is it, right?
Yeah. So if I go through here and I turn this into 10, it's going to sample more points. In fact, 1 every 1, right? And it looks a little better. And then I could go to 20 and then to 40, and eventually it will appear smooth, right? Is it actually every single point in that graph? No. Does it look like every single point in that graph? Yeah. So our eyes are not infinitely good, and there's not an infinite number of pixels, right? So line space differs from range only in, it has the start and the stop, just like the other one, but instead of how big a step, it's how many steps. And we like using both. Yeah. Right, yeah. So naturally, right? So here, if you have 100 steps, you've already said it, right? Whereas in range, you maybe don't know how many steps you're going to take. Let's say it's from 0 or 34 to 792 in steps of 1. You'd be like, oh shit, I have to take the subtraction of those two, whatever. But if it's 34 to 642 with 1,000 steps, then you know your list is going to be 1,000 elements long, right?
Okay, so another thing that we can do is we can also change the scales here. So do the same graph, right? And now we have a limit. So our y limit goes from negative 1.1 to 1.1, and it should show. Sorry, I did that one. It should show that again our 1.1 here, and then negative 1.1. I should actually do it shorter so you guys can see like the actual cutoff. I'm gonna do like 0.5 and 0.5. You should see a cutoff. Yes, so you can see here now this is our limits. It cuts off here where you specifically labeled it to cut off. Go back,
Yeah, go to like 10.
go to 10.
Yeah. Just to really mess with them, you know. Right?
So you see our scale here. Again, I also labeled it. Oh, sorry, change graph. So this is our one with the I was saying with our limit, and then this one I was changing here. You can see our labels. I added labels here. You have to import again. the specific X label and Y label, because the first time I ran it, it kept getting saying like X label is undefined, so you have to import it. And now you can see that they're labeled, our graphs are labeled in the X-axis and the Y-axis.
Okay, let's pause here for a second. There's a couple things I want to just like show you. If you scroll up, and the power of visualization, right? We're very intuitive people. As physicists, of course, we love to see the data. We can look for trends. What is, no, don't zoom in, don't zoom in.
Oh, my bad.
And you're good here. So here, scroll down a little bit. So here, one of the natural things to notice is that the scale really matters, right? Most of your plots, the first time they come out, they're going to be auto-scaled. And you can trick yourself into thinking there's nothing but a straight line there. So look at how, under bumpy this was compared to the first one. If the scale was 100, it would basically look like a flat line, right? So it's really important when you get your output, maybe you have one number that's like 692 and all the rest of them are normal. Now, the rest of the code might have worked perfectly good, but you can't tell because you didn't pay attention to what the boundaries are, right? Does it go between the values that you thought? When you made the calculation at the beginning and you got an order of magnitude of the size of the, like, let's say you're modeling how fast a ball moves after it's being kicked. Did you print out the very first value to make sure that it's not the speed of light? Right? So you want to pay attention here, not just here. Okay.
We can
Yeah.
also,
Could you, I know that, like, there's a line, is there also?
yeah,
Good question.
You would just have to label it. Here, you have to import it again, right here to xlim. And then you have to, again, add it to xlim here. So you'd have to, I like to put my xlim. You'd have to do this, right? Add xlim here, and when you're importing, and then again, give it a, like, a place, I guess. I don't know what it's called, like its own line. Yeah, and then again, it would show you the X limit too. If you guys want to see that, we could do that. We show 0 to 5. And there's 0 to 5.
Nice.
See. And then we can also further vary the graph, like you can to the plot function, we can add a third argument to change like specifics, I guess. So like in the first, so when you have plot X and Y, right, and then you add a third argument to it, which would in quotations, you would have G for green, right? And the colors are listed in where is it? On page 97 of your book. The colors are listed with like letters. So like R is red, RG is green, B is blue, C is cyan, right? And you can have it be a specific color of your graph. And then as you see the 2 dashes here, means a dashed line. If it's 1 dash, it's a solid line. You can have like if you put in an O, it marks the points with a circle and it doesn't connect them. Like you can mark points with a square if you put in S. I put K stands for black because like you wouldn't think like, oh, K means black. You would like put B, but B is blue. So that's why I have it there. It's like, okay, go back to reference that. Lastly, you can put in multiple graphs at once by adding subscripts to your different graphs. So I made here, I added the subscripts. So I did the same thing where I added the graph of Y equals sine X, right? In line space from 0 to 10 steps, or in 100, right? And then I plotted, I added a subscript to my Y equals sine X of 1, and then I added the 2 for my Y equals cosine X. And then I plotted exactly, X in the Y1, and then I had a black solid line, and then I plotted the second one with a such group 2, and then a red solid line, and then gave it limits, labeled it, and then here you have 2 different graphs, right? Yeah.
Okay, so before we move away from that, I want you to I'm gonna let you also show I'm gonna also show you some of the other colors that are possible. So if we just open up matplotlib colors, see how often I search this? Okay. So here's colors. And if you love colors, you're gonna love this. This is the list of all named colors. Here's your easy ones. Those are the ones that Kevin just talked about that are they're basically short keys. So you notice you don't have to do the word blue, you can just do B. But for every other color, you have to use the real name. And of course, how do you know that this is a legit programming language? How do you know that they're real?
Oh my God.
Wow.
See what that says? See what that says? Dodger blue. That's built right into the code. So if you want to use the best color, you got it right there, right? Do you see any others? No. I mean, maybe Red Sox, but that's not right. You get it?
Where's the red?
So if you fire brick. So for example, if you want a different color, you would say something like color equals, and then in quotations, that exact string. It's very important that it's that exact string. So if you, for example, capitalize it, it'll be wrong. If you put Dodger blue and there's a space in between the two, that'll be wrong. It'll get upset with you. You can name your own colors. Okay, let's relax. I didn't say they're perfect. They also have XKCD colors. This is really, I don't know if you guys know XKCD. You should probably be reading it if you're not nerdy enough. Become more nerdy. And they have some cool color tables. You'll also see if we go back and we just go to the color bar, you have color bar options. Oops, where'd it go? Here's matplotlib. It has many different types of color bars. So for example, when you start to color data, I don't know if you're going to show this. If I'm getting ahead of you, just stop me.
No, I didn't.
Okay. So when and we'll talk a little bit about using PyLab versus Matplotlib, just starting PyLab just to get the handle of it, but it's kind of like using math versus NumPy. You're going to get done with it fast and you'll move into Matplotlib. So by the time you do that, we start using what are called perceptually uniform sequential color maps. These are really important because what they do is they stack the brightest numbers, or sorry, the brightest colors with the largest numbers. So 100 is associated with the brightest, and 0 is with the darkest. So that's what we mean perceptually uniform. There is not peaks and troughs in brightness as you go from one side to the other. That's really important because if you look around you right now, that is what's happening. The brightest parts of objects are the parts that you're getting the most light from. That's where you're getting the most information from. And yet, some people love to use something called jet. So if, for example, I go into the matplotlib color bars, or sorry, the PyLab color bars, I'm going to show you one called jet, and it's horrifying. Okay, see this one here? Do you see why it sucks? If I ever see you use this, okay, why? It's got all the colors, right? We like rainbows. It's the modern era. No, that's not my problem with it.
There's like parts to it that's like more vibrant than others.
Yeah, there's bands right here. What the fuck does that mean? Okay, this is dark. This is dark. What the fuck does that mean? Okay, so you're headed towards here. You're like, oh, that's great. And then it becomes like weirdly bright and then dark and then bright. And you know what that does to an image? Makes it look horrible. So I'm going to show you. There's a Nature paper that I want you to read. Use of Color bars in science. And this is a paper written in 2020. And I want you, show me the figure. Okay, so here's the full-size image. Here is jet on the left. What is that image? That's the Earth. Does it look like the fucking Earth? No, it looks like garbage. This is black and white. You can at least understand that. Your brain has been wired to understand black and white imagery. As you go through life, you will find that many of your colleagues, especially male colleagues, tend to not be able to see as many colors as you might. And so therefore, they might need to use color bars that are more like this, that do not rely on this full, beautiful, vibrant spectrum, which doesn't give you a different additional information, right? Here's an apple. I don't need these extra information. That doesn't tell me shit, right? Over here, I can see that this apple has a chunk piece out of it, right? Here, I'm like, what is that?
Doesn't even look like an apple.
Doesn't even look like an apple, right? So I'll say this one time only. Don't use jet, but also read this. Okay, keep going.
So for scatter plots, they use a data set for scatter plots, so I stopped using my code and started referring to the book now.
Okay,
So
where'd it go?
okay, so for scatter plots, you would you can use two different methods, right? Where you can have a plot X, Y, and then black circles, like black O, which means it would produce black circles, or you can use scatter, the function scatter, like scatter parentheses X, Y, where it'll scatter these dots automatically. So in the book, there's a data set called the Hertzsprung-Russell diagram. And if you import these, so they use the shoot, I wish I had a laser pointer. So they took this data set here and labeled it, right? So they imported it and then they have it like stars.txt here. And then they use the function instead of plot, they use scatter. And they gave it its labels, temperature, magnitude, the limits, and then they put show, right? So when you run it, you would get this, right? And you can vary. See, that's all I really said on scatter plots.
That's okay. We'll use them a lot, right? So the only major difference here is that there's no lines connecting them, right? Obviously, when you're plotting data, in some cases, you want that extrapolating line between the data points, maybe if they're sparse. But if you're collecting data on a sample population, you want to see where all the points lie to see if you can draw the inference with your own eyes, right? As opposed to if these were connected just in the temperature that they were taken, they might do this all over the place and it might look like an absolute nightmare, right?
So I guess the point that I was trying to make with this one is that you can either input plot X, Y, and then the third argument would be quotation marks K and then O, which would produce something very similar like this, if not like very like the same. But you can also just write scatter X, Y, and it would be the same. Yeah. So I moved on from there to density. So for density plots where the colors and the brightness are used to indicate like the data values, I wrote I didn't have data sets, but I just put like from PyLab import this. I just put this right, and they had a specific data set that they used, and I wrote that this computer takes values from a data set and displays them here. And as the density of the area grow, like shows the areas with higher density as darker. And I wrote, if you see the graph on 103, you notice that the origin, the 0, is at the top left, right? And you can manipulate this by changing the argument to image show data here. If you see this here, you can change the argument to show image show data and then comma origin equals lower, and that would change the origin. It would flip it, right? It would change the origin from the 0 to the top left to the bottom left, as we're used to. I have, we can also change colors from black to others by adding a line before show. So here, oh, sorry.
Yeah, down?
Yeah.
Okay,
So
good.
here, so this is where I was saying, you can add image show data, the origin equals lower, and it would refer back to here instead of how they had it in the top left corner again. I also put that you can input different colors. So here, when they're importing again, you have to specify the color that you're importing. So they imported gray, and then the same thing from numpy import load text, which is your data file, right? And then the data image show, and then you have to put gray. You have to specify again, pull it from the import that you're doing. You have to put it there to show that you're.
And we won't necessarily go too deep into that one because we'll mess. Eventually, you should be able to, like, you can design your own color bars, which is fun because then it's like that's Kevin's color bar and he uses it for all of his plots, right?
I also wrote that there are a bunch of different color schemes for density graphs on matplotlib.org.
Yeah.
You can also add a function to have like a color bar slider, or not a slider, I'm sorry, like a color bar, so you can see like where, like what I don't know what
The values per color, yeah.
Exactly. So you can add that as a function. I don't know what page it's on. I just have it as a color bar parentheses, and it should have it on there.
It doesn't have an example here, but you'll see it. We'll get to it. Don't go into the 3D graphics. We're gonna basically ignore that.
Stop there.
Okay, good.
And then I also said that you can manipulate the graphs, right? So you can image show again, data origin equals the lower, and then you have an extent, right? I have where is it? I don't know where it is in the book, but I had a which will label your axes again from in a density graph. I have it as from in in order the beginning and end of the horizontal. So I have 4 values, right? So I have extent equals brackets 0, 10, 0, 20, right? So it shows in order from beginning to end is the horizontal, the beginning of the horizontal scale and the end of the horizontal scale, and then the beginning of the vertical scale and the end of the vertical scale. So that's what I listed as like important for your density graphs. You can also change the aspect ratio by adding again to the image show aspect at the end of all of that. You add a 107.
Yeah, you can change the sizes here, right? Same image, different scales.
Yes. Oh, yeah. So if you go on 107, yes. If you go on 107, please. So again, there's our extent right here, which lists the values of our I guess like our scales, right? And then again, you can change the aspect ratio, which again you would put it in your image show, all of that stuff again, and then you add aspect to the end, it would be your aspect ratio. And then yeah, that's all I have for density plot.
Cool. Any questions? Yeah. For what?
Okay. Or
just use the version actually for itself, or
so I understood it by like it is the scale that you have for your axes, right? So if it goes from right here 0 to 10, that means your x-axis, your horizontal axis will go from 0 to 10, right? And then I
Let's
don't know
show let's show an example here, right? So here is 0 to 500, 0 to 500, 0 to 10, 0 to 8, right? There is an x-lim, y-lim in images, right? There's only extent. So how much do you want to zoom into this image? Zoop. Then you put that there.
So the first two are the horizontal ones, and the second two
Yeah,
are
oh, the vertical ones, yes.
Cool beans? Okay, let's use it. Excited? All right, don't jump out of your seats. Let's pull this back over here. So who were you working with last week? Because you're no longer working with them.